Howdy everyone, and welcome to the Chapter 3 example problems. We'll take a quick look at some problems from this chapter, including converting between energy units, so joules and calories and that sort of thing. We'll look at heat capacity and calorimetry, determining how much energy is absorbed or released by some process. And then we'll finally look at specific heat to figure out for a specific substance how much heat is absorbed or released per gram and per degree Celsius to help identify that material. So let's get to it. Oops. There we are. So 3.51, in the problem set you have 52, so this will be a pretty good matchup. We are asked to convert, first in part A, 588 calories to joules. And so for that, we'll always want to look at our book to say, okay, what's the conversion there? And we'll find out for that one that 1 calorie is 4.184 joules. And with that equality, we can set up our dimensional analysis like we did in Chapter 2 and say, okay, 588 calories is our given. We'll multiply by the conversion factor. Calories goes on the bottom. Joules will go on the top. And then we can plug in our numbers. 1 calorie is 4.184 joules. And from that, okay, it's on top. We're going to multiply. Calories will cancel out. So 588 times 4.184. And we get that it's 2,460 point stuff joules. And I can leave it like that, because it's 3 sig figs. We're supposed to have 3. We have 3. It just worked out to be that 0. If we want to make it explicit, though, we got to leave it joules. Can't make it kilojoules. That would be convenient. So we could say 2.46 times 10 to the third joules, and then that way we know for sure. 3 significant figures, but still in joules. All right? So that's the first part A there. In part B, we want to go from 17.4 joules, this time to calories, but if we note, it's the big C calories. So this is the annoying thing with calories in the US. When it's calories with a capital C, that is the same as kilocalories. So we got to make sure we're watching out for that. So just as we had before, we know that, okay, 1 calorie is 4.184 joules. That'll get us there. Oh, but then for this kilocalories, okay, 1,000 calories is 1 kilocalorie. I'm going to leave it like that. I'll write it with the capital C at the end, but remember, kcal and capital C calories, same exact thing. So we have 2 conversions. That means we're just going to do 2 steps in our problem. So again, we start with our given 17.4 joules times our first conversion factor, joules on the bottom, calories on the top, so that things cancel out right. 1 calorie is 4.184 joules, so that will cancel that out. Now we'll do our second one to say, okay, we want to go from small calories to kilocalories, big C calories, and here it's 1 over 1,000, and that means calories will cancel out. So we're going to divide by 4.184. We're then going to divide by 1,000. So it's going to be a pretty small number. So 17.4 divided by 4.184, and then divided by 1,000, and we get 0.00. We want 3 sig figs again, so 4, 1. The next number's a 5, but after that's an 8, so it's going to round up 416. And we'll put big C calories, or kcal, same thing. Again, if you want to do scientific notation, you can make that 4.16. This time it's times 10 to the negative third big C calories. So this one, not going to break your diet, turns out. All right, so that's 51. You have 52 in your problem set. There's a few more. Just remember, if you're not sure, well, what number, where'd this 4.184? Look back in Chapter 3. There's a table that has all the conversions between the different energy units. So just use that to figure out, okay, what equals what, and then you can plug in from there. All right, next problem is 75. where we'll look at heat capacity and calorimetry. So for this one, it wants us to calculate the amount of heat required to raise the temperature of a 65 gram sample of water from 32 to 65 degrees Celsius. So for heat capacity calorimetry, we're saying, okay, how much heat based on what substance and what mass of it we have. So the equation we use for this to solve for heat, for anything really, is Q, how much heat, is equal to M, the mass, times the specific heat of the substance, times the change in temperature, the delta T. Let me try to get these time signs a little bit better. All right, so that's our equation. We just got to say, okay, if I'm solving for Q, that means I should be able to plug in a mass, a specific heat, and a delta T. All right, well, the mass is easy enough. Here it's 65 grams for water, so there's M. For the specific heat, they tell us, hey, it's water. So, from water, we look that up. There's a specific heat table. It's table 3.4 in the book. We look up pure water, and there's our favorite number from that last problem. Water is 4.184 joules per gram degrees Celsius. So there's the specific heat. We got the first two. Now for delta T, remember that, well, and we'll get this later in the book too. Anytime you see a delta something in this book, it's always final minus initial. So it's the final temp minus the initial temp. So we look here at the word problem. It says, okay, it's initially, delta T, at 32, but it's at the final, at the end, it's 65. So we do, okay, 65 minus 32, we end up with the 33 degrees Celsius delta T. So now we can take our equation and just plug that in. Say, okay, Q is equal to 65 grams, so coming from there. Next, specific heat, so we looked that up for water, 4.184 joules per gram degrees Celsius, times our delta T, which we subtracted over here, 33 degrees Celsius. And that's our setup. And if you ever want to double check, did I set this up right? Make sure the units cancel. I got a gram on top and a gram on the bottom. They'll cancel out. I've got a Celsius up top and a Celsius on the bottom. They'll cancel out. I got a joule on top that's not going anywhere, but hey, that means my answer will be joules, and that's energy. That's what we want. So that makes sense too. So that just means, okay, everything's going to multiply good. Let's just multiply it. And we say, okay, Q is equal to 65 times 4.184 times 33. So we get this big answer, 8,974.68 joules. And so I'm going to say, okay, I need 2 sig figs. So I want these first two. I cut it off. Okay, that stuff's going to round up. This is going to round off to 9,000. But then I say, okay, well, how can I, 9,000 joules. How can I show that that's only 2 sig figs? Because the 65 only had 2, the 33 only had 2. I can only show 2. So 2 ways. I could use scientific notation and say, okay, this is 9.0, there's my 2 sig figs, times 10 to the third joules. Or I could say, well, what would this be in kilojoules? I could use the metric system and say, oh, that's 9.0 kilojoules. So either one of these answers would have the 2 sig figs that we're looking for. And sometimes for a problem like this, pay attention to mastering chemistry. It might already have the joule entered in or the kilojoule. So if it does have joule, okay, then yeah, use this one with scientific notation. If it lets you pick, well, then pick whichever you find more convenient, whichever one makes more sense to you. But mathematically, these are all equivalent for those. All right, last one for this video, 3.85. 86 is again in the homework set, but here we'll do this example. It says we got an unknown metal. Don't know what it is. It's 28 grams. It absorbs 58 joules of heat. And when it does, the temperature rises from 31.1 Celsius to 39.9 Celsius. We want to get the specific heat of the metal, and then we want to identify it from table 3.4 to say, okay, which one does it match up to? This is like density. Specific heat is intrinsic intensive property. It should be the same no matter how much of a substance we have. So we're going to use the same equation from last time. We'll say Q is M times the CS times the delta T. But this time, we're going to solve for that. So if we want, we can go ahead and rearrange this and say, okay, the specific heat is going to be Q divided by M times the delta T. Okay? And so now we're going to say, okay, well, let's plug that in. Well, the Q is heat, and here we go, 58 joules of heat. There's my Q. M is the mass, and there we go, 28 grams is the mass. Again, delta T is the final minus the initial. So I'll just do that math down here real quick. Delta T will be the 39.9 degrees Celsius minus 31.1 degrees Celsius. And so that should be 8.8 degrees Celsius. That's my delta T. Okay, so that can plug in there. So now, okay, well, hey, I've got my three numbers. I can plug them in. Let's solve for it. So my specific heat will equal 58 joules over 28 grams times 8.8 degrees Celsius. Now this one's a little trickier to see, like, hey, do the units work out? They do, because all specific heats are energy per gram Celsius. So joules over gram Celsius, yeah, everything's in the right place. And you could maybe check the table when you're going to match up the numbers. It's like, hey, are the units the same as this table? Yeah, it will be. All right, so we go ahead and let's just do that math. So 58 divided by 28 divided by 8.8, and we get 0.2354. I'll just leave it there. Joules per gram degrees Celsius. For sig figs, we should only have 2 sig figs. All of these only have 2. So that would be 0.24 joules per gram Celsius. But I wanted to have this one here because this might match up to the book better. The table, I think, gives 3 sig figs, so I wanted to have that there. But this would be the answer you type in for what is the specific heat of the metal. It's right there. But now let's identify it. So I have the book handy here. I am looking at table 3.4. It's in section 3.11, talking about heat capacity and all that. And so there is one that is 2.35. It turns out 0.235 matches up with silver metal. So based on this answer, and there's nothing else in that table that's close. The next closest one is copper, but it's 0.385. That's way too high. And lead and gold are 0.128. That's way too low. This one matches perfectly. It's silver. So I think the book problem I gave you is a little different. It gives you a metal and says, is it this metal, yes or no? But you still got to figure out the specific heat first. So I hope that this video is helpful, especially with some of these heat capacity ones. Those tend to be the problems that trip people up the most. There might be a few others. I know I did see that there was a temperature conversion, which a Fahrenheit might sneak in there. Again, you use the equation from the book. You will not be having to do that on the test because Fahrenheit does not exist in our class other than homework problems that I can't change. But if you need help, again, come in for office hours, email, see the tutors, watch these videos again. With that, thank you, and I'll see you back for Chapter 4.